Hello everybody, this section is 6.4, the fundamental theorem of calculus. So we saw indefinite integral, so now we'll switch to definite integral. So the good thing is they're almost the same work, except there is something defined, which means the upper limit and lower limit for these integrals, and that will allow for the c not to be there. This constant will go away and you'll just find the value. Then we'll compare the two different integrals. So for the theorem 2 here, the fundamental theorem of calculus is if you have a derivative, if you have a function f to be continuous, so that's a key, number one, continuous. It has to be continuous and dot interval AB. Then if you see now we define the upper limit and the lower limit. The lower limit is A and the upper limit is B. So we say A lower limit, B the upper limit. F of x is the integrand. Integrand there. Then you're going to find an antiderivative like we did in the previous section. However, now you're going to find the values of these upper and lower limit and subtract them. And that's going to give you the value of this integral. So you'll find the antiderivative f, then you do f of b minus f of a, where f is the antiderivative of f, and f prime, of course, if you differentiate that, it should be this f of x. It's a nice, powerful theorem. It's useful. It makes things simple when it comes to these integrals. So let's look at, and of course, we're gonna do, you can do this bar here. There are different notations for this. Some do f of x this way, or with this bar here, they all mean the same thing. So let's explain here in this example 1, let R be the region under the graph, and for we have interval 1 to 3, so here A is going to be 1 and B is going to be 3. And let's use this fundamental theorem of calculus to find this calculation. But what does this mean, this integral? It means the area under the curve. So when you calculate the integral from 1 to 3 of f of x, which is x dx, you're finding the area under the curve. This has a bigger meaning in applications. It doesn't just mean we're finding an area under the curve and it's not useful. There is a lot of applications that use this to find specific functions or values. So the first understanding, of course, is that when you calculate this definite integral for a continuous function, interval 1 to 3, you're finding the area of under the curve. Look at it also this way. In this case, x is positive, this function is positive. So if this is positive, then you're finding the area under the curve. And if the function goes up and down, then it's going to be a net area. So let's just explain one at a time. So if we do this integral, we know the antiderivative of this is 1 plus 1 divided by 1 plus 1. It's x squared divided by 2. You usually do these antiderivative with c. But now you see when you substitute these values 3 and 1, the c will cancel, will be c minus c and it'll go away. So you see here plus c and c, so you'll have c minus c, so it'll go away, then you'll get just 4. And another way, of course, the elementary way, if we want to find this without the integral, of course, some functions it's not possible, but this one just to help. You could find the area of this rectangle here and the area of this triangle and add them up. Like this one, the 1, and this is 2, so it'll be 1 times 2 equal to 2. And this one here, the base is 2, so the area of triangle is half the base times the height, which is 2. And that's going to be 2. And if you add these, 2 plus 2, the total area is 4. And you can see that that's exactly the same as what the integral came up with. All right, so if we're able to calculate this area correctly and accurately, it will match the integral. And that's why the integral is much better, because if the curve something like this, then you can't come up with triangles and this stuff, right? It's not going to be easy to calculate stuff like this. And we'll see, of course, there is a method that's being used, and to divide this into so many regions and take the limit of it and all that. But just keep in mind, to help you understand this, this is a basic example to understand that the integral, the definite integral, calculates the area under the curve. So observe, of course, that's what I mentioned, and if we have another example, of course, with x squared, then if we integrate this from 0 to 1, and you see it's all above the x-axis, it's all positive, so that integration is going to give us the region R, which is under the curve. So 1/3 here, of course, you do the derivative and you substitute 1 and 0, and here f of b minus f of a, right, which is 1/3 times 1 minus 1/3 times 0, because b here is 1 and a here is 0, you get 1/3 for R, for that region R. So now that you know this fundamental theorem of calculus, you will add it to the indefinite integral and you calculate these. Just you want to make sure that it is the function is continuous over the interval. So this 1 to 3, we can split these to 2 different ones, and this one, the antiderivative is x cubed. This one is ex, so we will substitute 3, and we will substitute 1, and that's the integral, or the area under the curve. And one nice application from this is this measure of net of change theorem, because we saw something here. Let's go to it. We saw that if you have a function here as a derivative, then its antiderivative is its function same, right? So if you have a derivative inside, then you're finding the function as the antiderivative. So this will allow to use it directly into applications, because if you're finding a concentration or a population, you see you're using same variable. So if you say for a population n prime, then here it's going to be the population at some time or whatever b minus na, and of course here AB. So you see, if you have the rate inside, you can find the population between these two limits. So that's a nice thing that got picked up from this in this theorem of net change. Same thing for a concentration. You'll be having a concentration rate, and this allows you to find the concentration directly, right? Um, and here is an example for it. You can maybe pause the video and go through it. It's similar to all the examples we did with t equals 0 corresponding to 1970 and so forth, and this is period between 0 and 3. So I recommend kind of, pause the video and go through it. But I'll explain, of course, this part here. Since P prime is used, then P is the outside of 2 and 1, right? So if you have the function, then we'll do another example to this. If you have the given function here, so the 28th century for this Clark County in Nevada, and if you go to the keywords, the population was growing at a rate. You see the keyword, the rate. So that's the integral here is given the rate RT. So that's the keyword, right? So you can consider it prime, of course. So when you set up, it is coming here. And between 1 and 2, because the 1990 is going to be 2 and 1980 is 1, and again from 1970 is 0, and this is for decades, just like we did with the other examples. And go back and forth until it clears up. Then you move on. So this is a rate, that's why we put it there. And we know the rate is P prime, which is here given as some function RT. But when you put that in the integral, you're going to come up with P of whatever periods you want. We want 1990 and 1980. That's 2 decades after 1970. And 1970 is t equals 0. And of course, this uses decades, right? So the antiderivative is easy. You just do 2 plus 1, divide, which is 3, divide this number by 3. And same for the others, and you put t. You see here, no c is used because it cancels in the definite interval. No c is used because it cancels in the definite interval. And you just do the calculation as usual. We need this for 2. You calculate this for 2, and you're gonna calculate this again for 1, and you subtract them. Here they are, f of 2, which is here p of 2, and this is p of 1, right? And that gives us this. And so the net change is 278,371. So the net change between 1990 and 1980 is that number, right? Okay, so as so the net change formula um, is, if you have a rate there, then the outside is that function, and the evaluation here is down at the lower and the upper limits, and of course provided that f prime is continuous on AB.